Hello, and welcome back to the final speedrun of today with me, Vince. In this one, we're going to be going through Baynes' theorem, and finishing up chapter 11.1, so let's jump right in. So what is Baynes' theorem? So Baynes' theorem is derived from the fact that we already know that the probability of the intersection between two events is equal to the probability of one of the events times the probability that the other event occurs given that that one event occurred. And so therefore, if we have a set of mutually exclusive events, just A1, A2, A3, and so on, and of course the probability of A1 union A2 union A3 and so on is equal to the sum of their probabilities, probability of A2 and so on, and they are exhaustive events, which means that if two events are exhaustive, that means that this union is equal to 1. So this means that this probability should be equal to the u. And if we have an arbitrary event b, then we actually have the probability of one of these events happening, given that b happened, is equal to the probability of this event happening times the probability of b occurring given that this event happened, divided by the probability of b occurring given that the first event happened times the probability of this event of A1 plus the probability of b occurring given the second event, and so on. And so we can apply this theorem to solve many questions. So let's jump into some questions. So where are we? First, there are two jars with yellow and green marbles. In jar A, there are 5 yellow and 8 green, while in jar B, there are 2 yellow and 6 green. 2 marbles are transferred from jar A to jar B, and then 1 marble is taken from jar B. Find the probability that the marble drawn from jar B is yellow. And then, given that the marble drawn is yellow, find the probability that it was originally from jar A. Interesting question. Okay. So 2 marbles are transferred from jar A to jar B. And there are 5 yellow and 8 green marbles. So the probability that 2 yellow marbles were transferred what do we call it? The probability that 2 yellow marbles, I'll just put 2y, y2 maybe, are transferred is equal to 5 times 4, 20, over 13 times 12. The probability that 1 red and 1 yellow marble are transferred is equal to 5 times 8 times 2 divided by 13 times 12. And the probability that 2 red marbles were transferred is equal to 8 times 7 over 13 times 12. Now I'm just going to check that those probabilities add up. So we have 20 plus 5 times 8 times 2 plus 8 times 7, 156, 13 times 12, 156, right. So these are the correct probabilities. And so now we can use Baynes' theorem. So find the probability from the marble drawn from jar B is yellow. Actually, do we need to use it at this point yet? We don't need to use it at this point yet, because we'll use it here, but to find the probability that the marble drawn from jar B is yellow, we get each of these individual probabilities. So 20 over 13 times 12, 5 times 8 times 2, 80 over 13 times 12, 56 over 13 times 12. And so the probability that a yellow marble is drawn from here, when we add 2 yellow marbles, is 4 over 10, so 2/5. And then 3/5 that it's green. From this middle branch, the probability is 3 over 10, and 7 over 10, that means not. And from this bottom one, the probability is 2 over 10, 1/5, and 4/5, that it's not. So to get the probability that a yellow marble was drawn, we get 2/5 times 20 over 13 times 12. Or in other words, since we all have the base probability here, so it's 2/5 times 20 plus 3/10 times 80 plus 1/5 times 56 over 13 times 12. So we should end up with, what's 2/5 times 20? 8 plus 30 plus, we're going to have to multiply everything by 5, don't we? So 40 plus 30 times 5, 150 plus 56 divided by 13 times 12 times 5. So 40 plus 50 plus 100 plus 56. So I get 246 divided by 156 times 5, 780. Is that correct? Oh, it's, sorry, I messed up a calculation here because this should be 120, not 150. So since this is equal to 120, we actually have 216 over 780, and this simplifies to 18 over 65. So that's the probability that marble is yellow. Sorry about that, I'm back. So anyways, we're doing the second part. Yeah, given the marble draw is yellow, find the probability it was originally from jar A. So first we need to find the probability of a certain draw, say like of which marble, say the probability of y2, given that the yellow marble was picked. And in order to find this, we can then apply Baynes' theorem. So we have, this is equal to the probability of probability of y2 times the probability of y, given that y2 occurred, divided by the probability of y, given that y1 occurred, times the probability of y, and so on. So this is equal to, what's the probability of y2 occurring? It's 20 over 13 times 12. And then what's the probability of y occurring? Given that y2 occurred, it's 2/5. So it's over 2/5. And then when we divide this by, we do a similar thing for each branch. So it's 20 over 13 times 12 times 2/5 plus 80 over 13 times 12 times times 3/10 plus 56 over 13 times 12 times what's the probability? 1/5. And so this should all add up to 18 over 65. So now, Oh, I seem to have messed that up. Anyways, now where do we go from here? Well, we can cancel out the 13 over 12 in each one. And also we can cancel out the 5s. So we're just left with 80 times 3 over 2, which is equal to 40 times 3. So the probability that if it was yellow, and 2 marbles were drawn from the original one, is 40 over 20 times 240 plus 120 plus 56. And 40 plus 120 plus 56, we should know, is equal to 216. So this is the probability that we drew 2 yellow marbles, given that 1 yellow marble was picked. Now the probability that 1 was drawn is similar. We just replace this 20 times 2 with 40 times 3. So the probability that 1 red and 1 yellow were picked, given that a yellow was drawn, is equal to 120 over 216. And we can do the same for drawing 2 reds, except that we can actually skip this case, because if we drew 2 reds, that means that it's impossible that the original marble was from jar A. Now with these two, probability that we drew 2 yellows, we can simply multiply it by the probability that the marble was from the original jar. In this case, the probability of the yellow marble being picked being from the original jar is 1/2, and in this case it's 1/3. Since in this one 2 out of the 4 marbles were from the original, from jar A, and in this one 1/3 were. So this is equal to 20 over 216, and this one is equal to 40 over 216. So what I got is this is equal to 60 over 216, which is equal to, if we add them together, which is equal to, I think it's 10 over 36. Let me just divide 216 by 6. Yeah, 10 over 36. So this is what I got. The book gives a different answer, but I don't know why it gives it, and I think it's wrong this time. So on to the next question. And the next question is, we have 3 machines produce transistors. The first machine produces 50% of the transistors. The second machine produces 45% of the transistors. And the third machine produces 5%. 4% of the transistors from the first machine are defective, 3% from the second, and 8% from the third. Given that a randomly selected transistor is not defective, find the probability that the transistor was produced by the second machine. Okay, so we have the probability that the transistor was from the first machine, I'll call it A, is equal to 50%. The probability that it was from the second machine is equal to 45%. And the probability from the third machine is equal to 5%. Now the probability that it was produced, that it is defective, it's called D, given that it was produced from machine 1, is equal to 5%, no, 4%, sorry. The probability that it was defective produced from machine 2 was 3%, and the probability that it is defective when produced from machine 3 is equal to 8%, I think. So, given that a randomly selected transistor is not defective, find the probability that the transistor was produced by the second machine. So what we actually have to do is we have to convert these defective values into non-defective values. So this will be equal to 96%. Probability that it is not defective from B is equal to 97%. And the probability that it is not defective from C is equal to 92%. And so what we actually need to find is we need to find the probability that given that the transistor is not defective, find the probability it was produced by the second machine, which is B, given that D is not defective. So this will be equal to the probability of D not being defective of B times the probability of it being from B divided by the probability of it not being defective from A times probability of A plus the probability of it not being defective from B times the probability of B plus the probability of it not being defective from C times the probability of C. Okay, so we can calculate this. Now we just need to plug in all the numbers. So it's 0.97 times 0.45 divided by 0.96 times 0.5 plus 0.97 times 0.45 plus 0.92 times probability it came from C is 0.05. So this is all in all equal to times 0.45. So this is 0.4365 being divided by 0.96 times 0.5 plus 0.4365 plus 0.92 times 0.05 being divided by 0.9625. So this is around 0.4535, or in other words 45.35%. So it's around 45.35% that if a transistor was not defective, then it was from machine B. Okay, on to the final question. And the final question is, in a basketball squad, there are 12 players. In the squad, 4 players have a percentage shot of 0.9%. What? Like 0.9 of a percent? That doesn't sound right. But okay, cool. Horrible basketball squad. 4 players have a percentage shot of 0.6%, and the remaining players have a percentage shot of 0.2%. Imagine shooting and only making 1 out of 500 shots. That's what 0.2% means. A randomly selected player shoots a basket. Find the probability the player scores. Okay. Do we even have to use Baynes' theorem? No, we don't. This is just, since there are equal groups, the answer is the average of the 3. Because we have 4 players that shoot 0.9, 4 players that shoot 0.6, and 4 players that shoot 0.2. So to get the random probability from a random player, we would expect them to shoot the average percentage, which is 0.9 plus 0.6 plus 0.2 divided by 3, which is 0.567%. So we would expect them to make a shot. Yeah, it's actually correct. It's just 0.567%. So that's saying, oh no. So we expect them to have to take, on average, 176 shots for them to make a basket. Is that or like we would expect them within 176 shots to make 1 basket. That's horrible. Well, anyways, hopefully the speedrun wasn't horrible, and I hope to see you in the next one.